There are roughly 100 million black holes in the Milky Way, and we have found fewer than 50 of them. Let that sit for a moment. 100 million objects, each one a place where gravity has crushed matter so completely that nothing, not light, not radio waves, not any signal we can send or receive, escapes. They are scattered across a galaxy 100,000 light-years wide, and we have confirmed fewer than 50. That is not a rounding problem. That is not a gap we are close to closing. That is a census of almost total ignorance, and it is one of the strangest situations in modern science. Here is what makes this so strange. These are not rare objects. A star 20 times the mass of our Sun burns through its fuel in a few million years and then collapses, leaving a black hole behind. That process has been running in this galaxy for 13 billion years. The Milky Way contains somewhere between 200 and 400 billion stars. The math is straightforward. Massive stars have lived and died here by the hundreds of millions, and the collapsed remnants of those stars did not go anywhere. They are still here. They are everywhere. You are, right now, inside a galaxy absolutely packed with them. And yet, we can count the confirmed ones on 2 hands with room left over. The number is somewhere under 50, depending on how strict you are with the word confirmed. The gap between 100 million and 50 is not just large, it is almost mocking. It tells you something fundamental about what a black hole is and why finding one is so hard. The problem is simple in one sense and brutal in another. Black holes produce no light. A black hole sitting alone in empty space with nothing nearby to pull in and heat up is completely dark. No telescope picks it up. No detector registers it. It has a gravitational field, and that is genuinely all it offers the universe around it. If one drifted through the space between stars 1,000 light years from here, we would have no way of knowing. It would pass through, invisible, and keep going. What we have found, those few dozen confirmed cases, are the loud ones. The ones that happen to have a companion star close enough to steal gas from. When a black hole pulls material off a nearby star, that gas doesn't fall straight in. It spirals, flattens into a disk, heats up through friction until it reaches temperatures of millions of degrees and blazes in X-rays. Space telescopes can see those X-rays. That is how we found most of the black holes on the confirmed list. We didn't see the black hole. We saw what it was doing to the star next to it. That is a detection method with an obvious flaw. It only works when a black hole has a companion. Most black holes don't. The fraction of all black holes that happen to be in close binary systems, actively pulling gas and glowing in X-rays, is tiny. Maybe a few % at most. The rest are solitary, cold, and completely invisible to every instrument we have ever built. They drift through the disk of the galaxy, through the spiral arms, through the space between stars, and we have no idea where any of them are. Now think about what this means for the question in the title. How many black holes exist in the Milky Way? That number, roughly 100 million, doesn't come from counting. Nobody sat down with a telescope and tallied them up. It comes from calculation, from stellar population models and estimates of how many massive stars the galaxy has produced over its lifetime, and what fraction of those ended as black holes rather than neutron stars or white dwarfs. It is a statistical argument applied to a population that is almost entirely unobservable. It could be off by a factor of 10 in either direction, and we would have no direct way to know. So what we are really asking, when we ask how many black holes exist in the Milky Way, is something closer to this. We know roughly how many there should be, based on what we understand about stars. We know roughly where they should be, based on where stars form and die. We have confirmed a handful, and we are now, for the first time, beginning to develop methods that might actually let us find isolated black holes, the quiet ones, the dark ones, the ones with no companion and no X-ray flare to give them away. Gravitational microlensing, ultra-precise measurements of stellar motion, gravitational wave detections from mergers. Each method is beginning to pull black holes out of the dark, one at a time. This is going to be a long search. The galaxy is enormous. The black holes are invisible, and the tools we have are new. But the picture is starting to come together, piece by piece. And what it is showing us is a galaxy far more crowded with these objects than most people realize. The rest are out there somewhere, drifting through the galaxy in silence, and finding them is one of the strangest problems in modern astronomy. Before you can count something, you have to know what you are counting. The word black hole gets used constantly, but the actual physics behind it is stranger than most descriptions let on. It is not a hole in the way a pit is a hole. It is not empty space. It is a region where matter has been compressed so densely that gravity has become absolute. Absolute in the most literal sense. Nothing that enters can leave. Not gas, not light, not a signal of any kind. Whatever crosses the threshold is gone from the observable universe forever. To understand why that happens, you need escape velocity. Every massive object has one. To escape Earth's gravity, you need to be moving at roughly 25,000 miles per hour. The more massive or compact an object is, the higher that velocity gets. For a black hole, the escape velocity at a certain boundary has reached the speed of light. Since nothing travels faster than light, nothing can escape once it crosses that line. That boundary has a name. Astronomers call it the event horizon. The event horizon is not a surface you could land on or touch. There is no wall, no barrier, no visible edge. If you were falling toward a black hole, you would cross the event horizon without feeling anything unusual in that instant. Space looks normal from the inside of the crossing. What changes is your future. Once you are past it, every path available to you, every direction you could move, points inward. There is no trajectory that leads back out. You are not trapped the way a prisoner is trapped. You are trapped the way time is trapped moving forward. There is simply no other direction. Past the event horizon, in the models physicists work with, all the mass is concentrated at a single point, the singularity, a place where density becomes infinite and the equations of general relativity break down entirely. What is actually happening at a singularity is one of the genuinely open questions in physics. The math stops working, which usually means the model is missing something important. But whatever the singularity truly is, it sits at the center, and everything that enters the event horizon is falling toward it. Now consider the Sun. It is enormous. Over 1 million Earths could fit inside it. Its surface gravity is already 28 times stronger than what you feel standing on Earth. But the Sun is not a black hole because it is spread out across a vast volume of space. The surface is nearly 1,000,000 miles from the center. Gravity is strong, but it is not strong enough at the surface to trap light. What would it take to make the Sun a black hole? You would have to compress the entire Sun, all of its mass, down into a sphere roughly 3.7 miles across. That is smaller than most cities. At that density, the escape velocity at the surface would finally hit the speed of light, and the Sun would vanish behind its own event horizon. The solar system's planets would still orbit normally. Gravity at a distance does not change when you compress the object, but nothing could ever receive light from it again. That 3.7-mile figure is the Schwarzschild radius of the Sun. Every mass has one. Earth's is about 1/3 of an inch. A human body's is so small, the number is essentially meaningless in any physical sense. The point is that black holes are not exotic alien objects with different physics. They are what happens when ordinary matter gets pushed past the point where any force can push back. Now, the Milky Way does not contain just one kind of black hole. There are 3 categories worth knowing. The distinction between these categories matters because black holes of different masses behave differently and form through different mechanisms. Understanding the differences changes how you interpret observations and what those observations reveal about cosmic history. A stellar mass black hole reflects the life and death of a single star, while other types tell different stories about their origins entirely. The first is stellar mass black holes. These form when individual stars die in certain ways. They typically range from about 5 solar masses on the low end up to several dozen solar masses for the largest known examples. They are by far the most numerous type. When astronomers talk about 100 million black holes in the Milky Way, they are talking almost entirely about these. The second category is intermediate mass black holes. These sit in a range from roughly 100 solar masses up to somewhere around 100,000 solar masses. They are theoretically important because they may represent a middle stage between stellar mass black holes and the enormous ones found at galaxy centers. The frustrating thing is that confirmed examples are rare. Astronomers believe they exist, and the Milky Way is thought to contain somewhere between 1,000 and 10,000 of them. But pinning one down with certainty has proven difficult. This is one of the more persistent open problems in the field. The third category is the supermassive black hole. Every large galaxy appears to have one sitting at its center, and the Milky Way is no different. Ours is called Sagittarius A star. It contains the mass of roughly 4.3 million suns, packed into a region smaller than our solar system. It is not eating much right now. The galactic center is relatively quiet compared to the active galactic nuclei seen in other galaxies. But it is there, and it is real, and a later part of this story covers it in detail. For now, the thing to hold in your mind is the size difference between these categories. Stellar mass black holes are the remnants of single stars. Intermediate mass black holes are the size of a small star cluster's worth of mass compressed down. Sagittarius A star holds millions of solar masses in a space you could describe with the scale of our own solar neighborhood. These are not the same kind of object scaled up. They likely form through different processes and have different histories. Most of this story is about stellar mass black holes, the ones that form when individual stars die. because those are the ones filling the galaxy by the millions and the ones we are still trying to track down. Every stellar mass black hole in the Milky Way started its life as an ordinary star, just a very large one, not slightly large, not impressively large. We are talking about objects born with 10, 20, 50, sometimes over 100 times the mass of our Sun, sitting at the centers of young star-forming regions, burning so ferociously that they would exhaust in a few million years what our Sun will take 10 billion years to consume. The Sun has been quietly fusing hydrogen for nearly 5 billion years and is not even halfway through its fuel supply. A star born with 30 times that mass might burn through everything it has in 3 million years and then face something that no amount of energy can stop. Gravity. Pure, patient, total gravity. The story of how that happens is one of the most violent sequences of events in the known universe. It starts with hydrogen. Every star begins its life fusing hydrogen into helium in its core, releasing energy that pushes outward and holds the star up against its own weight. This balance, outward pressure from fusion against inward pull from gravity, is what a star is. Remove the fusion and the whole structure collapses. For most of a massive star's life, hydrogen does the job. But hydrogen does not last forever. When the hydrogen in the core runs low, the core contracts and heats up, and helium ignites. Helium fuses into carbon. The star has bought itself more time, but not much. Each new fuel source burns faster and leaves behind a heavier ash. Carbon ignites into neon and oxygen. Oxygen burns into silicon. Each phase is shorter than the last. Hydrogen burning might take millions of years. Silicon burning, near the very end, lasts about a day. Silicon burns into iron, and that is where everything stops. Iron is the endgame element in stellar physics. Every element lighter than iron releases energy when you fuse it. That is the whole basis of stellar power. But iron is different. Fusing iron does not release energy, it consumes it. When a massive star builds an iron core, it has reached a dead end. There is no next fuel. There is no new ignition. The core just sits there, growing heavier as the shells above it keep dumping more iron downward. When that iron core exceeds about 1.5 times the mass of the Sun, something happens that takes less than 1/4 of a second. The core collapses, not slowly, not gradually. In roughly 200 milliseconds, a ball of iron the size of Earth compresses down to a sphere about 10 miles across. The densities involved are almost beyond the reach of normal language. What happens next produces one of the most energetic events in the universe. The collapsing core overshoots, reaches nuclear density, and bounces. That bounce sends a shockwave outward through the star's outer layers, and when that shockwave tears through the surface, the explosion releases more energy in a few seconds than the Sun will release across its entire 10 billion year life. This is a core collapse supernova. From Earth, it can outshine an entire galaxy. The Chinese astronomers who recorded the supernova of 1054 watched a new star appear in daylight and stay visible for nearly a month. That explosion left behind the Crab Nebula, still expanding today, nearly 1,000 years later. Now here is where the mass threshold matters. What survives at the center after the explosion depends almost entirely on how heavy the original star was. For stars in roughly the 10 to 20 solar mass range, The collapsed core stabilizes as a neutron star. A neutron star is already one of the most extreme objects in the universe. City-sized, roughly 10 miles across, containing more mass than the Sun, so dense that a teaspoon of its material would weigh about 1 billion tons. But it holds together. The neutron pressure is enough to resist further collapse. For stars above roughly 20 to 25 solar masses, the story ends differently. The core is simply too heavy. Neutron pressure cannot hold it. Nothing can hold it. The collapse continues past the neutron star stage, past any density physics can support, and a black hole forms. The exact threshold is not perfectly pinned down. It sits somewhere between 20 and 25 solar masses, depending on the star's composition, rotation, and other factors. But above that line, there is no rescue. The supernova itself is not guaranteed either, and this is where things get strange. Most of the time, the explosion works the way the textbooks describe it. The shockwave forms, the outer layers get blasted away, and the collapsed core sits exposed at the center. But some very massive stars may not follow that script at all. If the star is heavy enough, or if the shockwave stalls before it reaches the surface, the explosion might fail entirely. Instead of a supernova, the whole star just falls inward. No blast, no flash, no expanding nebula lighting up the neighborhood for centuries. The star disappears, a black hole forms, and the only evidence is an absence, a star that used to be there and suddenly is not. Astronomers have a name for this. They call it a failed supernova, or sometimes a direct collapse event, and they have been watching for it. A team monitoring red supergiants in nearby galaxies found what looked like exactly this kind of event in 2009. A massive star in the galaxy NGC 6946, already nicknamed the Fireworks Galaxy because of how many supernovae it produces, simply vanished between one observation and the next. No explosion was recorded. When they looked at the position again, the star was gone. A faint infrared glow remained where it had been, consistent with dust heated during the event, but there was no supernova. The star had apparently fallen into itself. The object was designated N6946-BH1, and while scientists are still working through alternative explanations, the direct collapse interpretation remains the leading one. What this means for counting black holes is significant. If a portion of the most massive stars skip the explosion entirely and simply vanish, those black holes form without any signal. No burst of light, no expanding nebula to study later, no alert that anything happened at all. You would never know a black hole had formed unless you happened to be watching that specific star continuously and noticed it was gone. And across a galaxy containing hundreds of billions of stars, that is not a practical monitoring strategy. The direct collapse channel may account for a meaningful fraction of the most massive black holes in the Milky Way, and those are the hardest ones to find precisely because their births produced nothing memorable. The picture that emerges from all of this is one of enormous variety. Some black holes arrived with a brilliant announcement, a supernova visible across millions of light years, a flash that lit up the neighborhood for months. Others formed at the end of a long and complicated process in which the star ran through fuel after fuel, each stage shorter and more desperate than the last, before quietly losing the final battle. Some of the black holes in the galaxy may have formed in total silence, their progenitor stars simply vanishing from the sky one night with no explosion, no announcement, nothing. Here is the fundamental problem. A black hole sitting by itself in empty space produces no light, no heat, no radio emission, nothing at all that any telescope on Earth or in orbit can directly detect. That is not a limitation of current technology. It is not something a bigger mirror or a more sensitive detector will solve. It is physics. A black hole is a region where gravity has pulled so hard on the fabric of space that the escape velocity exceeds the speed of light. Nothing gets out. Not X-rays, not radio waves, not a single photon. The darkness is total and it is permanent. There is a theoretical exception. Stephen Hawking predicted in 1974 that black holes should slowly leak energy through a quantum process at their event horizons, a faint thermal glow now called Hawking radiation. For a stellar mass black hole, the temperature of this radiation is something like 100 millionth of a degree above absolute zero. The flux reaching any detector would be so vanishingly small that no instrument built by humans could measure it. Not today, not in any foreseeable future. Hawking radiation is real as a mathematical result, but as a detection strategy, it is essentially useless. It tells you nothing about where the black holes are. So picture what an isolated stellar mass black hole actually looks like from the outside. It is an object somewhere between 5 and 30 times the mass of our Sun, compressed into a sphere roughly the width of a small city. It drifts through the galaxy at whatever velocity it inherited from its parent star and whatever kick it received during the supernova that created it. It warps space around it. It has gravity, and it is completely, perfectly dark. No glow, no halo, no shadow you could photograph against the background sky. If one were drifting through the space between stars a few hundred light years away, and you aimed every space telescope humanity currently operates directly at it, you would see nothing. The patch of sky would look empty. The black hole would pass through your field of view, and you would never know. This is not a small problem. Remember the estimate. Roughly 100 million stellar mass black holes scattered through a galaxy roughly 100,000 light-years across. Most of them formed from stars that lived out their whole lives in isolation, collapsed, and went dark. Those black holes are still out there, still moving, with no companion to betray them and no surrounding gas to heat up. They are the vast majority of the population, and we have essentially no way to find them by looking. Now contrast that with what happens when a black hole is not alone. When a black hole is orbiting close enough to a normal star, gravity does something spectacular. The black hole begins pulling material away from the star's outer layers. That material does not fall straight in. It has angular momentum, so it spirals inward, flattening into a disk. Layers of gas inside that disk rub against each other as they orbit at different speeds, and that friction heats the gas. The temperatures in the inner regions of the disk reach into the tens of millions of degrees. At those temperatures, matter does not glow in visible light. It blazes in X-rays. The disk becomes one of the most energetic environments in the galaxy, pouring out radiation that space-based telescopes can detect from thousands of light-years away. This is the situation astronomers call an X-ray binary. One visible star, one hidden black hole, and a river of stolen gas connecting them. The black hole itself remains invisible, but the accretion disk surrounding it screams. It pulses, flickers, and sometimes releases jets of plasma moving close to the speed of light. The signal is hard to miss if you are looking in the right part of the electromagnetic spectrum. This is how the overwhelming majority of known stellar mass black holes were discovered. Not by seeing the black hole, but by seeing the carnage it leaves behind. Cygnus X-1 is the most famous example. In the early 1960s, before any telescope had been placed in orbit, rocket-borne detectors were lofted briefly above Earth's atmosphere and scanned the sky in X-rays. Earth's atmosphere absorbs X-rays completely, so ground-based detection is impossible. Those early rocket flights caught something bright in the constellation Cygnus, an intense source of X-ray emission with no obvious optical counterpart. When the first dedicated X-ray satellite, Uhuru, went up in 1970, it confirmed the source and showed it was flickering on timescales of milliseconds. That rapid variation told astronomers the emitting region was tiny, compact, smaller than a planet. Something very small and very massive was sitting inside all that radiation. The debate over whether Cygnus X-1 contained a black hole or a neutron star ran for years. What settled it was the companion star, a blue supergiant called HDE 2-26868, which turned out to be orbiting an invisible object with a mass s somewhere around 15 solar masses. A neutron star cannot exceed roughly 2 or 3 solar masses before collapsing further. Whatever HDE 226868 was orbiting was too heavy to be anything other than a black hole. Cygnus X-1 became the first object most astronomers were willing to call a confirmed black hole, and it got there entirely through the evidence of its accretion disk. The problem is that Cygnus X-1 is an exception, not a representative sample. X-ray binary systems require a very specific set of circumstances. Two stars must have formed close enough together to remain gravitationally bound. The more massive one must have ended its life as a black hole without completely disrupting the binary through the supernova kick. The surviving companion must be transferring mass at a rate high enough to keep the accretion disk lit up. Only a small fraction of all black holes were born into systems that met all those conditions. Estimates suggest that somewhere between a few percent and maybe 10% of all black holes have binary companions at all. Of those, only a fraction are actively accreting right now. Many binary black hole systems are in quiescence, meaning the mass transfer has temporarily stopped, the disk has cooled, and the system goes quiet. During quiescence, these systems look like ordinary stars. The black hole vanishes back into invisibility. Astronomers have catalogued somewhere around 50 confirmed or strongly suspected stellar mass black holes in the galaxy. Against a backdrop of 100 million, that is like finding 50 people in a country of 2 billion and declaring you understand the population. The known black holes are the loud ones, the ones with companions they are actively destroying, and they make up a tiny slice of the total population scattered across the galaxy. The first black hole humanity ever confirmed was not found by looking for darkness. It was found by looking at light, the wrong kind of light, in the wrong part of the sky, coming from a source nobody could explain. X-rays do not reach the ground. Earth's atmosphere absorbs them completely before they get anywhere near a telescope, which means that for most of human history, an entire wavelength of the universe was simply invisible to us. That changed in the early 1960s. Scientists started launching detectors on sounding rockets, short arcing flights above the atmosphere that lasted only a few minutes before falling back down. The instruments were crude, the flight windows were short, but in 1962, one of those flights detected something unexpected, a powerful source of X-rays coming from somewhere outside our solar system. The era of X-ray astronomy had started, not with a grand mission, but with a few minutes of data from a rocket that barely made it to space. By 1964, another rocket flight had swept across a region of the constellation Cygnus and found a source so bright in X-rays it stood out immediately. Astronomers called it Cygnus X-1, the first X-ray source catalogued in that part of the sky. It was intense, variable, and unlike anything they had a clean explanation for. When NASA launched the Uhuru satellite in 1970, the first X-ray telescope designed to operate in orbit for an extended period, Cygnus X-1 became one of the most studied objects in the sky almost immediately. Uhuru showed that the X-ray output was flickering on timescales of hundredths of a second. That was important. If a source of light is flickering that fast, the region producing it cannot be larger than the distance light travels in that time. Cygnus X-1 was producing enormous energy from a region only a few hundred kilometers across, at most. Nothing ordinary could do that. The next clue came from optical astronomers. Once the X-ray position was pinned down precisely enough, they could point ground-based telescopes at the same patch of sky and look for a visible counterpart. What they found was a massive blue star called HDE 226868 sitting right at the location of the X-ray source. It was a supergiant, roughly 20 to 30 times the mass of our Sun, and it was wobbling. The spectral lines in its light were shifting back and forth on a regular cycle, the classic fingerprint of a star being gravitationally yanked by an unseen companion. The orbital period was 5.6 days. From the motion of HDE 226868, astronomers could work backwards and calculate what the invisible object had to weigh. The answer kept coming out somewhere around 15 solar masses. The implications of that calculation were immediately clear to anyone who understood stellar physics. A neutron star, the densest object that physics allowed before crossing into black hole territory, had a strict mass limit. Theory predicted that neutron stars could not exceed roughly 2 to 3 solar masses before the pressure would overwhelm even the quantum forces holding them up. The invisible object pulling HDE 226868 through its orbital dance was 5 to 7 times heavier than the maximum possible for a neutron star. The math left no wiggle room for interpretation. Either astronomers had discovered something that violated everything they understood about the death of massive stars, or they had found something far more extreme. There was only one candidate left that could explain the observations. Not everyone accepted it right away. Throughout the early 1970s, a real debate ran through the astronomical community about whether Cygnus X-1 was actually a black hole, or whether some exotic, poorly understood object could account for the observations without invoking something as extreme as a singularity. Black holes at that point were theoretical. General relativity predicted them. Oppenheimer had worked through the math in 1939. But confirmation was another matter entirely. Many physicists were deeply reluctant to declare that a region of infinite density actually existed in nature based on a handful of X-ray measurements and an orbital wobble. The skepticism was not irrational. It was caution applied to an extraordinary claim. Kip Thorne was not one of the skeptics. By 1974, Thorne was convinced the evidence pointed clearly at a black hole. Stephen Hawking was not so sure, or at least he was willing to publicly play both sides. In what became one of the most famous wagers in the history of science, Hawking and Thorne made a formal bet. Thorne put his money on Cygnus X-1 being a black hole. Hawking bet against it. His reasoning was almost playful. He called it an insurance policy. He had spent years building a theoretical framework around black holes. If Cygnus X-1 turned out to be something else entirely, at least he would win a magazine subscription. The bet was written down and signed. It sat there for 16 years. During those 16 years, the evidence only deepened. Better satellites, sharper measurements, more careful modeling of HDE 2.26868's orbit all pointed the same direction. The mass of the unseen object was not shrinking under new analysis. If anything, tighter observations pushed it higher. The accretion disk model, where gas stripped from the companion star spirals inward and heats up to millions of degrees before plunging past the event horizon, explained the X-ray variability with a precision that competing models could not match. By the late 1980s, the consensus among most researchers was no longer seriously in question. Cygnus X-1 was a black hole. It had been one all along. What the Cygnus X-1 story established was not just the existence of one black hole. It established a method. The approach: find an X-ray bright source, identify its optical counterpart, measure the orbital dynamics, calculate the mass of the invisible object, and compare that mass against the maximum possible for a neutron star, became the template for every stellar mass black hole discovery that followed. The dozens of X-ray binary black holes confirmed in subsequent decades were all found using variations of the same logic that astronomers worked out while arguing about Cygnus X-1 through the 1970s. Hawking eventually conceded the bet in 1990, signing over a year's subscription to a certain magazine, and the object that had started as an anomalous bright spot on a detector became the foundation of an entirely new field. The number 100 million does not come from counting black holes. It comes from counting everything else and working backward. After decades of confirming a handful of black holes, the loud, bright, X-ray blazing kind, astronomers faced an obvious problem. The confirmed population was tiny. The galaxy is enormous. Something had to bridge that gap, and the bridge turned out to be mathematics rather than observation. Start with the galaxy itself. The Milky Way contains somewhere between 200 and 400 billion stars. That number is itself an estimate, derived from measuring stellar densities in different regions and extrapolating outward. But it is a reasonably well-constrained estimate, and it gives astronomers a foundation to work from. The question is, what fraction of those stars are massive enough to end their lives as black holes? Not every star can become one. A star like our Sun will eventually swell into a red giant, shed its outer layers, and leave behind a cold, dense remnant called a white dwarf. That is the fate of the majority. Black holes require something much more extreme. The threshold is roughly 20 solar masses. Stars above that limit burn hotter, faster, and more violently than anything in our Sun's league. They tear through their hydrogen in millions of years rather than billions. When they finally run out of fuel and collapse, the core is too massive for any known force to halt. Neutron star formation requires a collapsing core below roughly 2 to 3 solar masses. Above that, the collapse keeps going and a black hole forms. So the calculation becomes a question about how many stars in the Milky Way have ever crossed that threshold. That is where the initial mass function comes in. The initial mass function is one of the most important relationships in all of stellar astronomy. It describes how stars are distributed by mass when they form. The pattern is consistent across nearly every star-forming region astronomers have studied. Small stars vastly outnumber large ones. For every star with 20 times the Sun's mass, there are thousands of stars with roughly the Sun's mass, and millions of stars smaller than that. The curve drops steeply as mass increases. Massive stars are genuinely rare. But the galaxy has been forming stars for 13 billion years, and rare things add up when you have that much time and that many raw materials. Plug the initial mass function into a model of the Milky Way's star formation history, and you can estimate how many high-mass stars have been born over the galaxy's lifetime. Star formation was not constant. The early galaxy produced stars at a frantic rate. Things have quieted down considerably since then. Astronomers model this history using observations of stellar populations at different ages, chemical abundances in old and young stars, and the current distribution of stellar remnants. When you run those numbers, the fraction of stars massive enough to become black holes is somewhere around 1 in 1,000. Apply that fraction to the total number of stars that have ever formed in the Milky Way, and you land near 100 million. This is called stellar population synthesis. It is the same general approach astronomers use to model distant galaxies, predict the chemical evolution of stellar populations, and estimate the abundance of other rare stellar remnants. The technique is well tested. It produces results that match observations in the cases where observations are possible. But it rests on assumptions at every step, and those assumptions carry real uncertainty. The initial mass function, for instance, may not be perfectly universal. There is evidence it behaves differently in extreme environments, very dense star clusters, or regions with unusual chemical compositions. The threshold between neutron star and black hole formation is not a hard line either. It depends on the internal physics of the collapse, which is genuinely complicated, and on the rotation and magnetic field of the progenitor star. The star formation history of the Milky Way is well constrained in broad strokes, but fuzzy in the details. And there is a subtler problem. Not every massive star that collapses necessarily produces a black hole with the expected mass. Some may shed tremendous amounts of material through stellar winds before they ever collapse, leaving a remnant too LIGO to qualify. Metal-rich stars in particular tend to lose more mass this way. All of those uncertainties stack. The 100 million figure is the middle of a wide range. The low end of serious estimates sits around 10 million. The high end reaches toward 1 billion. That is a factor of 100 between the floor and the ceiling, which is a remarkable spread for a number that gets cited with such confidence in astronomy headlines. The reason it still gets cited is that the middle of the range is genuinely informative. Even if the true number is 50 million or 200 million, the conclusion is the same. There are a staggering number of black holes out there. The vast majority are invisible, and we have confirmed only a tiny fraction of them. What makes this method powerful is exactly what makes it limited. It is statistics applied to an invisible population. You never see most of what you are counting. You infer its existence from what you know about the processes that created it and the objects that are similar to it. A forensic accountant reconstructing finances from partial records is doing something similar. The records are incomplete, the methodology is sound, and the answer is probably in the right ballpark. But you would not stake everything on the last 2 digits. Astronomers are in the same position with black holes. The confirmed population, fewer than 50 stellar mass black holes with reasonably well-measured properties, is a sample so small it barely represents the range of what should be out there. Each one was found because it happened to have a companion star close enough to feed from, or happened to pass in front of a background star at the right moment. The quiet ones, the isolated black holes drifting through the galactic disk with nothing nearby to reveal them, are not in the count. They are in the model. The honest answer is that this estimate could be off by a factor of 10 in either direction, and nobody will be able to correct it until we find a way to detect black holes that are not actively eating something. At the exact center of the Milky Way, hidden behind curtains of gas and dust, something sits that contains the mass of 4 million suns compressed into a region smaller than our solar system. You cannot see it with your eyes. You cannot see it with an optical telescope aimed at that patch of sky. This was because the galactic center is wrapped in so much gas and dust that visible light never makes it through. The region sits roughly 26,000 light-years away in the direction of the constellation Sagittarius. It is one of the most chaotic environments in the entire galaxy. Young, massive stars orbit there in tight clusters. Ancient stars trace slow ellipses through a region dense with gas clouds and magnetic fields and high-energy radiation. Everything in that neighborhood is moving fast and being pulled by something enormous that produces no light at all. The first hint that something unusual lived at the center came from radio astronomy. In 1974, 2 astronomers named Bruce Ballack and Robert Brown were using a radio interferometer to map the galactic center region when they spotted a compact, incredibly bright radio source sitting almost exactly at the geometric center of the Milky Way. It was tiny, far too small to be a cloud of gas. It radiated with a consistency that suggested something gravitationally extreme. They called it Sagittarius A star. For years, astronomers debated what it actually was. The leading hypothesis was a supermassive black hole. But a hypothesis is not a measurement, and the evidence at that point was circumstantial. What changed everything was stars. If you want to weigh an invisible object, you watch what orbits around it. This is the same logic that lets astronomers weigh planets and measure the mass of our own sun. The problem at the galactic center was that the stars orbiting Cygnus A were moving so fast, in such tight orbits that tracking them required resolving features at incredibly fine angular scales, across 26,000 light-years through all that dust. 2 independent research teams took on that challenge and spent decades at it. Reinhard Genzel at the Max Planck Institute in Germany and Andrea Ghez at UCLA each built programs to track individual stars at the galactic center using large telescopes equipped with a technique called adaptive optics. That corrects in real time for the blurring effects of Earth's atmosphere. Year after year, they watched. The stars moved. The orbits took shape. One star in particular became the key to everything. Designated S2, it follows an elliptical path that brings it swinging close to Sagittarius A every 16 years. That is a remarkably short orbital period for a star. By comparison, it takes our solar system roughly 225 million years to complete one orbit around the galaxy. S2 finishes its entire loop around the galactic center in the same time it takes a child born today to finish high school and graduate from college. When researchers calculated the mass needed to produce that orbit at that speed and that distance, the answer was clear and unambiguous. The object at the center of S2's orbit contained approximately 4.3 million times the mass of our Sun, and based on the precision of the positional measurements, that mass was packed into a region far too small to be any collection of ordinary stars. Nothing in known physics other than a supermassive black hole could account for it. Genzel and Ghez shared the 2020 Nobel Prize in Physics for this work, alongside Roger Penrose, who had proven decades earlier that black hole formation was a fundamental consequence of general relativity. But a Nobel Prize for tracking stars is not quite the same as a photograph. And for decades, the actual visual confirmation of Sagittarius A remained out of reach. Then came the Event Horizon Telescope. The EHT is not a single telescope. It is a network of radio observatories spread across multiple continents, including instruments in Chile, Hawaii, Spain, Greenland, Antarctica, all synchronized to observe the same target at the same moment. By combining the data from all of those dishes, astronomers effectively created a telescope with a dish size equal to the diameter of Earth itself. This is called very long baseline interferometry. The resolution it achieves is extraordinary. Imaging Sagittarius A from Earth using the EHT is roughly equivalent to photographing a donut sitting on the surface of the Moon. In May 2022, the collaboration released their result. The image shows a bright, fuzzy ring of radio emission surrounding a central dark region. That dark region is the shadow of the black hole, the zone where the gravity is so extreme that no light escapes. The bright ring is produced by hot, glowing gas swirling just outside the event horizon, heated to extreme temperatures as it spirals inward. The image matched almost exactly what the equations of general relativity predicted for a 4.3 million solar mass black hole at that distance. It was the second black hole ever directly imaged, following the 2019 image of the far more massive black hole at the center of the galaxy, Messier 87. Sagittarius A star does not look like an active monster. Compared to the supermassive black holes in other galaxies that are actively consuming enormous amounts of material and blasting out jets of energy across hundreds of thousands of light years, our galactic center is quiet, calm even. Sagittarius A star is mostly dormant. It occasionally flares when a small amount of gas drifts close enough to get pulled in. But these are minor events. The energy output of Sagittarius A today is so low that it barely registers compared to what is typical for supermassive black holes elsewhere. Our galaxy has what some astronomers describe as a sleeping giant at its center. But sleeping is not the same as always having been asleep. The evidence suggests that Sagittarius A star has not always been this quiet. X-ray observations of the gas clouds surrounding the galactic center have revealed something puzzling. Some of those clouds are glowing in X-rays in a way that only makes sense if they were illuminated by an intense burst of radiation at some point in the past. The clouds are too far from Sagittarius A to be responding to current activity. They are responding to something that happened long ago. The light travel time tells you roughly when. The answer points to an event around 200 years ago, meaning that sometime in the early 1800s, Sagittarius A star underwent a brief but violent active period, tearing through a significant quantity of infalling material and flooding the surrounding region with radiation. No one alive at the time had the instruments or the understanding to know it was happening. Recent X-ray observations suggest that roughly 200 years ago, Sagittarius A star briefly woke up and tore through whatever material happened to drift within reach. The light from that feeding event is still echoing through the surrounding gas clouds today. 100 million is a large number, but the Milky Way is an incomprehensibly large container. The galaxy stretches roughly 100,000 light-years across. Its disk is a flattened spiral of gas, dust, and several 100 billion stars. If you tried to drive across it at highway speed, you would need something in the range of 1 trillion years to finish the trip. Spreading 100 million black holes across that volume sounds dense until you actually do the math. On average, you get roughly 1 black hole for every few cubic light years of space. The nearest one to you at any given moment is probably hundreds of light years away. These objects are not swarming around us. They are scattered through an almost unimaginably large structure, and their distribution across that structure is far from random. Black holes tend to settle where the stars that made them were born. This is not complicated physics. A star spends its life in a particular place. It dies in roughly that same place. The remnant, whether neutron star or black hole, inherits the address. So the first thing to understand about where black holes live is that they trace the history of star formation in the Milky Way. Dense star-forming regions produced more massive stars. More massive stars produced more black holes. The galactic disk, where the spiral arms carve through clouds of gas and dust, has always been the most active nursery for massive star formation. That is where the majority of the galaxy's black holes ended up. Most of those 100 million objects are almost certainly embedded somewhere in that disk, spread across the arms and the spaces between them, orbiting the galactic center at speeds of hundreds of kilometers per second. But the distribution is not flat. It thickens dramatically toward the center. As you move inward toward the galactic core, the density of stars rises steeply. The central bulge packs billions of old and young stars into a relatively compact volume. More stars means more generations of stellar death, more supernovae, more remnants. A process called dynamical friction pulls compact objects inward over time. When something dense and heavy moves through a background of lighter objects, it experiences a kind of gravitational drag. It loses energy. It sinks. Over billions of years, stellar mass black holes gradually migrate toward the center of the gravitational well. The galactic center acts as a slow drain, and black holes trickle toward it across cosmic time. Current estimates suggest that roughly 25,000 stellar mass black holes may have accumulated within a single parsec of the galactic center, which is about 3.26 light years. That is an extraordinary concentration. 1 parsec is a region smaller than the distance between our Sun and its nearest stellar neighbor, and it may contain tens of thousands of black holes packed into that space, all orbiting within the gravitational shadow of Sagittarius, a star. This creates a region near the center unlike anything in the outer galaxy. Dense clusters of black holes, neutron stars, and massive young stars, all sharing a relatively tight volume. The interactions between them are complex. Black holes there can form binary pairs. They can merge. They can be captured or ejected by close gravitational encounters. Astronomers have only begun working out what that environment actually looks like in detail, and the picture keeps getting stranger with each new observation. Move outward from the center and the density drops off. The disk of the galaxy follows a profile that falls exponentially with distance from the center, with a scale length of roughly 3 kiloparsecs. That means as you move about 10,000 light-years further from the center, the density roughly drops by a fixed fraction. The outer spiral arms are not empty, but they are sparse compared to the inner galaxy. Star formation still happens out there. Massive stars still form and die, but the rate is lower, and the history of star formation in the outer disk is thinner than in the inner regions. Fewer black holes per unit volume as you move outward toward the galactic edge. Then there is the halo. This is the part of the picture that surprises people. The galactic halo is the vast, roughly spherical region that surrounds the disk. It is mostly empty by disk standards, populated by old globular clusters, ancient stars on wide orbits, and the remnants of smaller galaxies the Milky Way has consumed over billions of years. The stars in the halo are old. They formed early in the galaxy's history, when the available gas was mostly hydrogen and helium, with very little of the heavier elements astronomers call metals. This matters because a star's metal content affects how much mass it sheds during its lifetime. Metal-rich stars like those in the disk drive powerful stellar winds that blow off significant fractions of their mass before they die. Metal-poor stars hold on to more of their mass. A metal-poor star that starts at 30 solar masses dies at something closer to 25 or 28 solar masses. That heavier remnant is more likely to collapse into a black hole rather than a neutron star, and if a black hole does form, it tends to be heavier than those produced by metal-rich stars. This matters for binary black holes specifically. Models suggest that around half of all binary black hole systems in the galaxy may reside in the halo and in the satellite galaxies orbiting the Milky Way, precisely because the low metallicity environments there were better at making the kinds of massive stars that left behind heavy remnants. The disk produces more black holes in raw numbers, but the halo produces a disproportionate share of the most massive ones. So the galaxy does not have a single black hole population. It has layers, a dense cluster near the center, a broad population scattered through the disk, a diffuse but surprisingly significant contribution from the ancient halo. The black holes are not evenly spread. They cluster toward the center, thin out toward the edges, and pile up in specific regions where the conditions for making massive stars were historically favorable. The most elegant way to find a black hole that is not eating anything is to wait for it to walk in front of a star. That sounds almost too simple. But it is built on something real, something that falls directly out of Einstein's general relativity. Mass bends space. When light from a distant star travels through curved space near a massive object, the path of that light bends toward the object. The effect is the same as a glass lens focusing light, which is why astronomers call it gravitational lensing. When the alignment is close to perfect, the lensing object acts like a magnifying glass, and the background star suddenly appears brighter than it really is. The brightening is temporary. The lensing object keeps moving, the alignment fades, and the background star dims back down. This entire event, from first brightening to return to baseline, can last anywhere from a few days to a few months, depending on how massive the lensing object is and how fast it is moving. The shape of the brightening curve is not random. It follows a very specific mathematical profile, and hidden inside that profile is information. The peak brightness tells you how close the alignment got. The width of the curve tells you about the relative velocity between the lensing object and the background star. The duration is tied to the mass of the lensing object. If you can measure all of this carefully enough, you can work backward and estimate what you are actually looking at, even if you cannot see it directly. This is called gravitational microlensing, and it is one of the few tools astronomers have for detecting objects that produce no light at all. The challenge is that these events are rare. Most stars never produce a microlensing event on any human timescale. To catch them in useful numbers, you need to watch an enormous number of stars simultaneously and wait. The logical place to look is toward the center of the galaxy. The galactic bulge is packed with stars, and anything drifting through the foreground between Earth and that dense background population has a reasonable chance of drifting across the line of sight to one of them. 2 surveys have spent decades doing exactly this. OGLE, the Optical Gravitational Lensing Experiment, run by the University of Warsaw, has been monitoring tens of millions of stars toward the galactic bulge since the early 1990s. MOA, a Japan-New Zealand collaboration, runs a parallel survey from a telescope in New Zealand. Together, these programs have catalogued tens of thousands of microlensing events. Most of them are unremarkable. An ordinary dim red dwarf passes in front of a background star. The star brightens briefly, and the event is logged and archived. Interesting to statisticians, not headline news. But a small fraction of those events behave differently. They are longer, wider. The mass implied by the curve is too large to be any normal star. And some of these events show something that regular stellar lensing does not produce, an astrometric shift, meaning the apparent position of the background star moves slightly as the lensing object passes. The size of that shift depends on the mass of the lensing object and its distance. When you combine the photometric curve with the astrometric signal, you have a much tighter grip on what you are dealing with. This is where Hubble becomes essential. Ground-based telescopes can catch the brightening, but measuring the tiny positional shift of a star requires a level of precision that only space-based optics can deliver. In 2022, a team using years of Hubble follow-up data announced something remarkable. A microlensing event first flagged in 2011 by the MOA survey, designated MOA-2011-BLG-191, had finally yielded enough data to characterize the lensing object conclusively. The team had been tracking it for over 6 years with Hubble, measuring the slow drift of the background star's position as the lensing object pulled it out of alignment. When the numbers came together, the mass of the lensing object came out to roughly 7 solar masses. It was dark, no companion star, no X-ray emission, nothing visible at any wavelength. The conclusion was difficult to argue with. This was an isolated stellar mass black hole drifting through the galaxy. It was the first time one had ever been directly confirmed through microlensing, and the first time a lone black hole had been identified without any binary companion or accretion disk to betray its presence. The black hole has since been given the designation OB110022. It is drifting somewhere about 5,000 light-years from Earth, entirely alone, entirely dark, giving nothing away except a brief bend in starlight a decade ago that a patient survey happened to catch. It is worth pausing on what that patience actually required. The initial brightening event lasted a few months in 2011. That alone was suspicious, longer than most stellar lensing events. But a suspicious microlensing curve is not a confirmed black hole. To separate a black hole from a heavy neutron star or an extremely faint white dwarf, you need the astrometric signal, and that means years of Hubble observations, tracking a positional shift measured in fractions of a millisecond. 1 millisecond is roughly the angle subtended by a coin sitting on the surface of the Moon, viewed from Earth. The precision required is extraordinary, and this single confirmed event took over a decade from detection to publication. This is the bottleneck. Ground surveys can find hundreds of candidate events per year. The ones that look massive enough to be black holes number in the dozens annually. But following each one up with the depth of Hubble observation needed to confirm the mass takes time, telescope hours, and years of data reduction. The confirmed population of isolated black holes found this way is still tiny. Not because they are rare in the galaxy, because confirming them one at a time with a single space telescope is glacially slow. That is exactly what makes the Nancy Grace Roman Space Telescope so significant to this field. Roman is a NASA observatory with a wide field of view roughly 100 times larger than Hubble's, and one of its core survey programs is designed specifically to monitor the galactic bulge in a way that no previous telescope has matched. It will watch roughly 100 million stars simultaneously with the cadence and resolution needed to catch microlensing events and begin extracting astrometric signals far faster than any previous approach allowed. The numbers astronomers project are striking. Where current surveys confirm perhaps 1 or 2 isolated black holes per decade, Roman is expected to identify dozens. The prediction is not that it will find black holes by accident, but that it will find them systematically, building a statistical sample large enough to actually constrain the mass distribution of isolated black holes across the galaxy. That sample matters enormously. Every confirmed isolated black hole adds a data point to the question of how black holes are distributed in mass, in space, in velocity. It tests the stellar evolution models that produce the 100 million estimate. It checks whether direct collapse events really happen, whether the kick velocities from supernova-born black holes are large or small, and whether the spatial distribution of lone black holes matches what the simulations predict. Right now, all of that is essentially unconstrained because the confirmed population is too small to draw conclusions from. Roman changes that. The Roman Space Telescope, once operational, is expected to catch thousands of microlensing events per year, and among them, astronomers predict, will be dozens of isolated black holes finally giving themselves away through nothing more than the bending of light. In September of 2015, Two black holes roughly 1.3 billion light-years away finished a billion-year spiral toward each other and merged in a fraction of a second, and for the first time in history, humanity felt the ground move. Not metaphorically, the ground actually moved. Two detectors in the United States, one in Louisiana and one in Washington State, each measuring the distance between a pair of mirrors suspended 4 kilometers apart, registered a change in that distance smaller than 1,000th the width of a single proton. Think about that. A proton is already so small that any comparison to everyday objects becomes almost meaningless. And the signal that passed through those detectors was 1,000 times smaller still. Yet the instruments caught it. They caught it because the people who built LIGO, the Laser Interferometer Gravitational Wave Observatory, had spent decades getting those mirrors stable enough, those lasers precise enough, those sensors quiet enough to hear something that should by any reasonable measure have been impossible to detect. The signal lasted less than a second. It had been traveling for over 1 billion years. What LIGO actually detected was a ripple in space-time itself. Not a wave moving through space the way light does. A wave that is space, stretching and squeezing the fabric of the universe as it passes. Einstein predicted this in 1916 when he published his general theory of relativity. He also thought the waves would never be detected, that they would be too faint, that no instrument humans could ever build would be sensitive enough. He was wrong about the second part. Gravitational waves are produced whenever massive objects accelerate. Two stars orbiting each other produce them. A single spinning asymmetric object produces them. But by far, the most powerful sources are the final moments of two compact objects, black holes or neutron stars, completing their long spiral and colliding. In those last fractions of a second, the energy pouring out as gravitational waves exceeds the combined light output of every star in the observable universe. And it all passes through you without you feeling a thing, or almost without you feeling a thing. The event that LIGO caught in September of 2015 was later designated GW 150914. The two black holes involved had masses of roughly 29 and 36 solar masses. They merged into a single black hole of about 62 solar masses, and the missing 3 solar masses were radiated away as pure gravitational wave energy in under a second. 3 times the mass of the Sun, converted entirely into ripples in space-time and flung across the universe. The signal that reached Earth was a chirp, rising in frequency and amplitude as the two objects spiraled faster and faster before slamming together. When physicists played the data as an audio file, it sounded like a brief rising tone, almost like a bird call. The countdown nobody expected. It arrived at the Louisiana detector first, then 7 milliseconds later at THE Washington detector. That tiny delay told the team the approximate direction the wave had come from. The match to Einstein's equations was near perfect. Here is what made physicists stop and stare. Those black holes were heavy. X-ray binary systems, the source of almost everything previously known about stellar mass black holes, had suggested a typical mass range of roughly 5 to 15 solar masses. The black holes in GW 150914 were 29 and 36 solar masses. That was not supposed to happen under the standard picture. Stars that massive were expected to shed enormous amounts of material through stellar winds during their lifetimes, leaving behind smaller remnants. The fact that two such heavy black holes existed and had found each other raised immediate questions. Were these black holes formed in a low metallicity environment, where stellar winds are weaker and stars retain more mass before death? Were they originally a stellar binary, two massive stars born together? Or had they formed separately and paired up through gravitational encounters in a dense star cluster? The merger had answered one question and opened a dozen more. More detections followed. By the end of the first observing runs, the catalogue of confirmed gravitational wave events had grown to nearly 90, almost all of them black hole mergers. The mass distribution was strange. Some mergers involved black holes in the expected range of 5 to 20 solar masses. Others involved objects of 40, 50, even 85 solar masses. One merger, detected in 2019 and designated GW190521, involved a final black hole of roughly 142 solar masses, putting it in the intermediate mass range that astronomers had been hunting for through other methods. The diversity was not what anyone had cleanly predicted. The universe appeared to be making black holes across a much wider mass range than the sample from X-ray binaries had indicated. That earlier sample had been deeply biased. X-ray binaries show you the black holes that are actively accreting in relatively tight orbits, with companions bright enough to detect. They are not a fair census. Gravitational waves are different. They do not care whether a black hole has a companion. They fire off at the moment of merger and travel in every direction at once. LIGO does not work alone anymore. The Virgo detector in Italy came online in 2017, and the Kagra detector in Japan joined the network after that. Multiple detectors working together do something a single instrument cannot. They triangulate. When the same wave arrives at different detectors at slightly different times, the time delays pin down the region of the sky the wave came from, shrinking the error box from a broad stripe across the sky to something closer to a patch. That localization is what allows optical telescopes and radio arrays to search the right region for any electromagnetic counterpart to the merger. With neutron star collisions, this follow-up has found the kilonova afterglow, the glowing debris cloud of freshly forged heavy elements. With black hole mergers, there is usually nothing to see, because nothing escapes. But the localization still matters for understanding where in the universe these mergers are happening and what kind of galaxies they prefer. What the full catalogue of detections is building, event by event, is a statistical portrait of black holes that no other method can produce. X-ray binaries gave astronomers a sample of dozens of black holes over decades of searching. Gravitational wave detectors are adding confirmed mergers at a rate of several per week during active observing runs. Each detection carries the masses of both objects, the mass of the final merger product, the spin parameters, the distance. Stacked together, these data are sketching the shape of a population, and the shape keeps coming back heavier, broader, and more varied than the models built before September of 2015 had expected. The detectors are getting more sensitive. The next generation of instruments, including proposed underground observatories with arm lengths of tens of kilometers, will push the detectable volume out far enough to catch mergers happening almost anywhere in the observable universe. Every merger detected since has added another data point to a growing picture of a universe containing far more black holes and far more massive ones than earlier generations of astronomers had assumed. The closest known black hole to Earth is not a dramatic X-ray blaze or a celebrated gravitational wave source. No telescope caught it devouring a companion star. No detector felt the ground shake when it formed. It was found because a perfectly ordinary star in the constellation Ophiuchus was wobbling. That wobble is the whole story. The star in question is a G-type star, the same broad category as our own Sun. Unremarkable in almost every way. Medium temperature, medium brightness. The kind of star that shows up by the thousands in any decent survey of the galaxy. But when scientists ran the data from the European Space Agency's Gaia satellite through careful analysis in 2022, they noticed something wrong with its path through space. It wasn't traveling in a straight line the way a solitary star should. It was tracing a small, repeating ellipse. Something invisible was pulling it in a tight loop, roughly every 186 days, and that something had a mass of around 10 times our Sun. Gaia was not designed to hunt black holes. Its mission is astrometry, the precise mapping of stellar positions and motions across the sky. Over the course of its operations, it has tracked the movements of more than 1 billion stars, measuring their positions to an accuracy that is genuinely difficult to put into human terms. We're talking about detecting an angular shift equivalent to watching a coin change position from across a continent. That level of precision is what made the discovery possible. You don't need a black hole to be eating something to find it this way. You just need it to be close enough to a star that the gravitational pull is measurable. And with Gaia watching 1 billion stars at once, the odds of catching that kind of signal improve enormously. The black hole is now designated Gaia BH1. It sits roughly 1,560 light-years away, which in galactic terms is essentially next door. The entire Milky Way is about 100,000 light-years across. Gaia BH1 is close enough that, by comparison, it's sitting on our front step. Yet nobody had found it before. No X-ray signal, no unusual brightness, nothing. Just a star moving strangely and a telescope precise enough to notice. Follow-up observations confirmed what Gaia had hinted at. Ground-based spectrographs measured the radial velocity of the companion star, the way its light shifts toward red and then toward blue as it orbits. Those measurements match the Gaia prediction almost exactly. The invisible companion mass came in at roughly 9.6 solar masses. Far too heavy to be a neutron star, which tops out around 2 to 3 solar masses. There was no plausible explanation other than a black hole. Astronomers announced the discovery in November 2022, and it immediately claimed the title of nearest confirmed black hole to Earth. Then, a few months later, the same team found another one. Gaia BH2 sits about 3,800 light-years away, also in a quiet corner of the sky, also paired with an unassuming companion star. This one is a red giant rather than a sun-like star. The orbital period is longer, around 1,300 days. The black hole mass came in at roughly 8.9 solar masses. Same method, same discovery path, same verdict. A black hole hiding in plain sight, detectable only because it was nudging its neighbor through space. Both discoveries created immediate questions, and not small ones. Standard models of stellar evolution predicted that these systems shouldn't exist. When a massive star collapses into a black hole, the core collapse and associated supernova should release an enormous asymmetric kick, and that kick should tear the binary system apart. The companion star should be flung free, leaving behind an isolated black hole rather than a bound pair. Some simulations suggest that even when a supernova doesn't fully destroy a binary, it should leave the companion badly disrupted, chemically enriched by the explosion, contaminated with elements from the dying star. The companion stars in Gaia BH1 and Gaia BH2 show none of that contamination. They look pristine. They look like nothing violent happened anywhere near them. That is genuinely strange. It means either the supernova was much weaker than standard models predict, or the black hole formed through something closer to direct collapse, the star simply shrinking inward without producing a major explosion. If that second explanation is correct, it has implications for how common these quiet systems might be. A dramatic supernova throws light across the galaxy and announces the birth of a compact remnant. A direct collapse does not. The black hole simply appears. The companion star continues on its orbit, unaware, and the whole system drifts through space, putting out no unusual signal at all. How many of those systems are out there? That is the uncomfortable question sitting at the center of these two discoveries. Gaia has only analyzed a fraction of its full dataset. The complete data release will cover a far larger number of stars with far more detailed motion measurements. If two systems turned up in the early analysis, the expectation among researchers is that the final catalogue could reveal dozens or more, maybe many more. The companion stars in these systems look like ordinary stars because they are ordinary stars. They are not being eaten. They are not being irradiated. They are not showing any sign of distress. The black hole sitting beside them is just there, massive and invisible, completing its orbit like clockwork. The fact that Gaia has found two of these systems in a relatively short time suggests that black holes sitting quietly beside ordinary stars may be far more common than anyone previously guessed. Between the stellar mass black holes and the supermassive monsters, there is a gap in the catalogue that has bothered astronomers for decades. On one side, you have stellar mass black holes, the remnants of dead stars, ranging from a few solar masses up to perhaps 100. On the other side, you have supermassive black holes like Sagittarius A star, clocking in at millions or billions of solar masses. The middle ground is where intermediate mass black holes should live. Hundreds of solar masses, thousands, maybe tens of thousands. The math says they should be there. The observations keep coming up nearly empty. This is not a minor bookkeeping problem. It matters because intermediate mass black holes are almost certainly the missing chapter in how supermassive black holes got so large. Sagittarius A star contains the mass of 4.3 million suns. It did not get there by swallowing one star at a time. Something had to provide the seeds, dense, massive objects that could sink to the center of a young galaxy and grow. Intermediate mass black holes are the leading candidate for what those seeds were. If they existed in large numbers in the early universe, the math of how supermassive black holes assembled starts to work. If they did not, the origin story of every galaxy center becomes a lot harder to explain. The Milky Way itself is estimated to contain somewhere between 1,000 and 10,000 of them. That range tells you something honest about the state of the field. It is not a tight measurement. It is a theoretical bracket built on stellar population models and assumptions about dense star clusters, and it could be wrong in either direction. What makes this especially frustrating is that intermediate mass black holes should not be rare objects hiding in exotic corners of the universe. They should be forming right now in the dense hearts of globular clusters, where stars pack together tightly enough that collisions and mergers happen on timescales short enough to pile up mass fast. Globular clusters are one of the best places to look. These are ancient, tightly bound collections of hundreds of thousands of stars orbiting the Milky Way like satellites. Several of them show something interesting when astronomers measure stellar velocities near their centers. The stars are moving too fast. Not slightly fast, noticeably fast, in a way that suggests something heavy is sitting in the middle pulling on everything nearby. The globular cluster M22 is one example. The velocity dispersion in its core is consistent with a central object somewhere between a few thousand and maybe 100,000 solar masses. But velocity dispersion alone is not a confirmed detection. It is a gravitational fingerprint without a face. The problem is that ruling out alternatives is hard. A dense collection of stellar mass black holes packed into the core of a cluster can produce a similar velocity signal. Neutron stars can contribute. You need to distinguish between one large invisible object and a swarm of smaller ones, and right now, the resolution required to do that cleanly is at the edge of what current instruments can manage. Some studies have argued for a central massive object. Other studies using different data have argued the same signal can be explained without one. The debate has been running for years. Ultraluminous X-ray sources offer another avenue. These are X-ray sources found in nearby galaxies that shine far brighter than any single stellar mass black hole should be able to manage, assuming it is pulling in gas at a reasonable rate. Some of them are bright enough that the most natural explanation is a black hole in the intermediate mass range, somewhere between a few hundred and a few thousand solar masses, actively accreting material. A handful of these sources have been studied in detail. The evidence is suggestive in several cases, but the interpretations are contested and confirmed. Airtight detections remain stubbornly rare. One candidate stood out for years in the globular cluster 47 Tucanae. Radio and X-ray measurements pointed toward a central compact object. Then deeper observations complicated the picture. Another candidate in the galaxy, NGC 1313, produced an X-ray signature that looked consistent with a black hole of roughly 5,000 solar masses. These signals are real. The argument is over what is producing them. Intermediate mass black holes are not confirmed simply because the data fits. The data has to rule out every other explanation too, and that bar keeps being difficult to clear. What the field needs is a detection method that does not depend on the black hole actively eating something. Most of the best evidence so far comes from objects that happen to be accreting gas or happen to sit in clusters where stellar velocities can be measured. The vast majority of intermediate mass black holes, if they exist in the numbers the models predict, are sitting quietly in the halos of galaxies or the remnants of dissolved clusters, producing no X-rays, no obvious stellar wobble, nothing that current surveys are designed to catch. Gravitational waves change that calculus. When two intermediate mass black holes spiral together and merge, they produce a gravitational wave signal in a frequency band that sits below what ground-based detectors like LIGO can hear. LIGO is tuned for stellar mass mergers. Supermassive mergers fall in a completely different range. Intermediate mass mergers fall in between, in the millihertz band that only a space-based detector can access. LISA, the space-based gravitational wave observatory planned for the 2030s, is expected to detect mergers involving intermediate mass black holes at distances so vast that it should finally settle the question of how common they really are. The honest accounting of what we do not know about black holes in the Milky Way is longer than the accounting of what we do. That is not a failure of the science. It is just an honest description of where things stand when you are trying to census a population of objects that produce no light, drift through a galaxy 100,000 light-years across, spend most of their existence doing absolutely nothing detectable. The 100 million figure gets repeated constantly. But it is worth being clear about what that number actually is. It is not a count. It is a calculation built on assumptions about stellar masses, star formation rates, how often massive stars successfully collapse into black holes rather than neutron stars. Change those assumptions slightly and the number shifts. Some models come back with 10 million, others push toward 1 billion. The true population could sit almost anywhere inside that range. Right now, there is no observation that can settle the debate. The mass distribution is another open problem. It turns out to be a stranger one than astronomers expected. For decades, the stellar mass black holes found in X-ray binaries clustered in a fairly narrow range, mostly between 5 and 15 solar masses. Then gravitational wave detections started arriving, and the picture got complicated fast. The first confirmed merger involved black holes of roughly 36 and 29 solar masses, producing a combined object of about 62 solar masses. That was surprising. As more detections came in, the mass range kept expanding. Black holes of 50, 70, even 85 solar masses appeared in the data. These numbers do not fit neatly into the standard models of how massive stars end their lives. Either the formation pathways are more varied than the textbooks describe, or there is a population of black holes that grew through previous mergers, or both things are true at once. Nobody has fully resolved this. Then there is the question of quiet formation. Some massive stars may simply collapse without producing any visible supernova at all. The outer layers fall inward. There is no explosion. The star just disappears. Astronomers have identified a handful of candidates, massive stars in nearby galaxies that seem to vanish from survey images without any recorded outburst. If direct collapse is common, it has two consequences. First, it means a fraction of the galaxy's black holes were born in total silence, with no supernova kick. That affects how they are distributed across the galaxy. Second, it means the formation rate estimates are uncertain in ways that are hard to correct without catching more stars in the act of vanishing. Surveys are watching, but the events are rare enough that confirmed cases remain frustratingly few. The binary companion problem runs deeper than it looks. Almost every confirmed stellar mass black hole was found because it was actively pulling gas from a companion star close enough to feed the accretion disk. Gaia changed that slightly by finding black holes orbiting companions through gravitational wobble alone, without any X-ray signature at all. But the systems Gaia can detect require companions bright enough, and wobbles large enough to register in the astrometric data. Wide binaries where the companion is small, dim, or very far from the black hole are still essentially invisible. How many of those exist is genuinely unknown. The early Gaia results suggested the number could be surprisingly large. But translating those early results into a firm population estimate is still ongoing work. Sagittarius A star sits at the center of this catalogue of uncertainties in its own category. It is dormant now, but the X-ray echo evidence showing it tore through surrounding material roughly 200 years ago is a reminder that dormant and inactive are not the same thing. Whether it will feed again in any timescale relevant to human civilization, nobody can honestly say. The feeding depends on whether any cloud of gas drifts close enough to fall within reach. The galactic center environment is chaotic enough that predicting this is not yet possible. What astronomers do know is that Sagittarius A star is not uniquely quiet. It is simply in a quiet phase. Quiet phases in supermassive black holes can end. Intermediate mass black holes sit in their own unresolved corner of the problem. Between stellar mass objects and supermassive ones, there is a range where objects should exist in meaningful numbers, forming in dense star clusters, possibly seeding the growth of larger black holes over cosmic time. The Milky Way is estimated to contain somewhere between 1,000 and 10,000 of them. But confirmed detections are rare enough that those bounds are barely constrained by actual observation. The signals that would indicate their presence, unusual velocity distributions in globular clusters, unusually bright X-ray sources with characteristic spectral signatures, are real but ambiguous. LISA may eventually settle this by detecting mergers involving these objects at distances where no other method could reach. The deepest uncertainty is about the current state of the population itself. Black holes do not just sit still, they merge. A binary black hole system that formed 8 billion years ago may have already merged once or twice, building up a remnant far more massive than either original object. The 100 million estimate counts black holes as if the galaxy's history is a simple ledger of stars that lived and died. But the actual population has been evolving through mergers, through accretion, through the complex dynamics of a galaxy that has been consuming smaller galaxies for billions of years. The real number, whatever it is, belongs to a system still in motion. The last decade changed this field more than any decade before it. Gravitational wave detection went from a theoretical ambition to a routine catalogue. Gaia started turning up black holes through astrometry. Microlensing surveys found the first isolated black holes confirmed through direct mass measurement. The Event Horizon Telescope produced actual images of objects that most physicists 50 years ago were still debating the existence of. 10 years ago, the count of confirmed stellar mass black holes in the galaxy stood at around 20. Today, it is closer to 50, with more arriving every few months. The rate is only accelerating as new instruments come online and new detection methods mature.